Ladies and gentlemen, thank you very much and welcome for the afternoon session. I'd like to talk a little bit on what's happening in Germany on 6G. We heard a lot on what's happening on the European level. Colin gave an introduction this morning, so I'd like to use the time of the 20 minutes to focus on what we are doing in Germany. I mean, we heard a lot of motivations. What are the, let's say, the differences, what 6G will bring us when we move from 5G via 5G advanced into a new era of technology and solutions. It should be really human-centric, should consider certain requirements of the society, so it should serve the society as a whole. And therefore, certain parameters like sustainability and usability are really, really important. So basically, we want to move from where we came from data and data communication to really integrating sensing of data, using the sensing data, and also incorporating computation into the network, into the overall system. And that brings us to new horizons. I mean, how to do that? We've heard a couple of directions where we go. Higher frequencies is one topic. Why? Because there is a tremendous amount of spectrum available, unused. So far, it was not easy to be addressed. And with the higher frequencies, we will have smaller antennas. Smaller antennas allows us to put more complex arrays into a certain aperture or space, so it has a form factor fitting into devices, into base stations. So that will be a straight way forward. I will come back to that, where we can go into that area, more antennas and up to terahertz, subterahertz frequencies. And then the other end is really reducing the communication system in the latency space. For 5G, we had 1 millisecond as a target. In reality, if you have the network performance involved and so on, we are in the order of a few milliseconds in reality. In 6G, we want to go beyond that. And then there is another aspect, really, how to deploy the network. So far, it's a terrestrial network, what we have available worldwide. It has base stations above ground, a couple of 10 meters in altitude, and then we have users usually distributed in buildings or on the ground. In the future, when considering drone traffic as vehicles in the future to do transport or even taxiing people from one place to the other, we need coverage in the third dimension. And our current networks are not made for this. So we really have to rethink and handle this. And then we can also deploy base stations in the third dimension on high altitude platforms, integrating satellites, low orbit or medium orbit satellites into the whole system. So it will be a three-dimensional deployment of base stations and users, and that's something where we have to provide the enablers for. So having talked about this, then one important aspect which was mentioned by others here is that 6G is expected to provide intelligence and sensing capabilities. Intelligence, so AI will be a native part of the 6G system, and sensing is that all these antennas with their spatial resolution can serve additional purposes. And that means we can expect that 6G will bring high resolution channel sensing and feedback for the system in the directional and delay domain. And that allows then smart interference-aware radio resource management and scheduling. And again, that provides ubiquitous coverage everywhere, anytime. If we know where the users are, we can point beams towards the user depending on the demand of capacity coverage of particular users. And that will change the whole network design tremendously. And we heard about the drivers. I'm not going into that too much. We heard about these use cases. So some new applications will be these extended reality applications with haptic feedback or holographic displays. And all these applications based on massive and wideband sensing. Within the time I have, maybe let me focus then on what's happening in Germany. We have a big 6G program started recently. Hans Schotten yesterday made reference to that. So we have the 6G platform Germany, and this should really serve to enable digital sovereignty for the citizens in a hyper-connected world. So that's the title and the purpose of this platform. And within this platform, we have 4 major research hubs on 6G. One of them, the left one, is 6G, the Research and Innovation hub or center in Berlin. I come to that in a minute. We have 6GEM, 6G Live, and the Open 6G hub. To give you an idea, all these hubs, each hub is funded over 5 years with about 70 million euros. And it's fundamental research, predominantly directed to universities, research centers, and in collaboration with industry. And to give you more insight in what we are doing with the 6G RIC cluster in Berlin, which started last year. I mentioned this on the last summit in 2021. So you see the partners are distributed across Germany. So we collaborate with the different research entities. And in this hub, we focus on 6 technology innovation areas, which basically will be the focus of this hub. Other hubs will have other focus. So one is really going to higher frequencies, enabling this, going into the subterrahertz domain for mobile access. And another one is intelligent radio environments. And I will give an example. So that touches reconfigurable intelligent surfaces, how we can integrate them potentially into the environment to have a better, let's say, or a reconfigurable radio propagation environment. Then network as a sensor. The name is saying what this is all about. Then we have the 6G connectivity. It's towards massive connectivity for IoT in 6G by joint consideration of data generation, information processing, transmission and processing. So basically you can do a lot of processing of redundant data over the air already. So these concepts go into that. And then we have other topics towards post-quantum security by design. A very hot topic. We have other funding schemes in Germany and Europe, and autonomous convergent networks. That's really very close related to AI-based automation of the system and have these disaggregated 6G networks. And for all these technologies areas, we will have demonstration within the project with partners. So stay tuned for the next years what's happening there. And in order to make this really meaningful and impactful, we have close association with industry partners. So we have an advisory board, we have these industry partners, we invite them a minimum once a year to go into close discussion, share the project results and get feedback. And the other way is also to go into the related fora, like NGMN. We recently had a presentation of the project and other fora you see on the right-hand side of this slide. And let me now go into topics we research in Fraunhofer in more detail. I selected 2 of them due to the limited time frame we have. One is really going from millimeter wave to subterahertz communication. You have directed of the beams. You have a lot of bandwidths, short range, so you can have provide a dense network, for instance, in a production environment. And you have a lot of advantages you see there. You can have a point-to-multipoint network with directional transmission, large bandwidths, low latency. Interference is interesting. You have low interference to neighboring systems because you're well separated by walls of a production hall, and you're pretty immune to jamming and eavesdropping because of the large bandwidths you're using. And really moving then to the subterahertz domain, I presented that we last year had a first success together with our colleagues from LG Electronics. So we worked on 150 gigahertz carrier frequency, and we could show a real live transmission over 100 meters over the air in Berlin. And that's what it looked like. You see, like, the transceiver design was rather bulky and large for a first proof of concept, but it worked. And based on this, we continued the collaboration, and we shrunk the size and capabilities of the system. And meanwhile, we recently reported a tripling on the distance. We now could transmit from one building to another over 300 meters. And that's quite interesting. And further features I just want to mention is we embedded really a 5G-like SSB-based channel beam identification. So you have the transmit beams identified with an SSB identification, and the receivers, then they can be switched in turn. They can check what's the best transmit beam per receive pair. And what's really interesting, you see on the right-hand side, we could move the receiver, and then depending on which channel pair is the best, we had a handover from different beam pairs to others. And with the overlap of the beams, we had a continuous transmission between the transmitter and the receiver. And more important, maybe that's of interest for you, because many people are skeptical if subterahertz transmission is suitable really in environments, and if that works. If we lose the line of sight, I can tell you, if you block the line of sight, and then other beam pairs on large reflections or strong reflections on the wall could take over the transmission, the link. And the interesting point is that these alternative links were, in comparison to the line of sight, usually in that environment 6 to 7 dBs weaker. And that's not much. That's within the modulation encoding scheme we can provide in a cellular system. So I'm very confident that also with higher frequency we can create reliable communication with subterahertz. And if we talk about reflections on the wall, then the question is, do we want to be dependent on what's there and what's given, or do we want to shape propagation environments as well? And that's the interesting part with these reconfigurable intelligent surfaces. Basically, these allow us to identify certain taps of coming from reflecting clusters. And if we put on these positions a tunable reflector, then we can basically shape the reflective properties of this particular place and also provide coverage to other areas. How does that work? Basically, you transmit to a surface, and this surface is tunable and can change, as one example, the reflective angle. So that's one way you can change phases and things like this. There are many ways to do that. And if you do that, then you can use it for different purposes. So you can create an alternative path if a line of sight is blocked, if needed, to a certain area. That's the left picture we see here. You can create, let's say, multiplexing gains in a certain environment, and other options which are a bit more, let's say, academic at the current point of time. Now, the question is how to bring this into a certain maturity that in 3-4 years' time we can bring that into the standard. And we looked into that because there is a lot of research, but how to integrate this into a standardized system, there is still quite limited research results available. So what's in the end important is these multi-risk scenarios and multi-operator scenarios, because it's wideband, it's a passive reflector. So basically whatever wave goes into will be reflected depending on the current configuration state. And we looked into this, and you see on the right-hand side in this bubble all these areas where it touches on. We need channel feedback. We have to identify which multipass tap is related to a reconfigurable intelligent surface. Because if we know that, we can use this tap and the observation to control the risk elements. And so we need extensions of the existing framework we have in our systems to really do that, and then we can do improved interference and beam management. And that will be then basically the input to the RIS, which might be fall also into the framework of a network-controlled repeater. Here the RIS is a repeater with zero amplification, and therefore it could be put into that context in the future. That's what we believe. That's a little bit on how that looks. On the right-hand side, you have these elements, you have a RIS controller, and that's connected to a network. And depending who is deploying this, is this a joint deployment of different network operators or by one, but it has an effect on the other networks. So they have to be controlled with a database. You need inter-network, let's say, feedback. These are all things we have to provide. And that would also allow then to point maybe a particular beam onto this RIS panel, and then depending on the state, you might change your SSB number on the pointing beam. So for a user, this behaves transparent. It's distinguishable if he sees the one setting of the RIS or the other setting of the RIS. And providing this feedback allows then the network, the base station, to learn where the users are, what are the preferred settings, so you can use the resources in an efficient way. And if you do that with different operators, then one preliminary result is that if operators have a co-deployment on the same mast with similar antennas, then these RISs have a similar effect on their network and improvement, and that's really a very beneficial thing to share RISs among such operators. And in order to really evaluate this, we have a simulation environment which allows then to strategically deploy these RISs and evaluate what extra coverage they provide, and then based on that, put them onto strategic positions, on the best positions in the network. In order to stay within the framework of the time, we have seen all these many slides before. Here you see the 6G projects we have in Europe, and the next talk will be by Emilio on RISE 6G on these RISs as well. So basically the takeaway is that we expect key concepts and technology drivers for 6G to be hybrid machine learning and AI for the RAN, to exploit the domain knowledge and learn slow changing features, exploit high frequencies, go to analog to information, integrated RF design, converge sensing, communication and computing, customize the radio environment, have these intelligent reconfigurable elements in the network, energy efficiency is important, integrate security, and then have critical and massive MTC provided in the system. That concludes my talk. Thank you very much.